It really is a great pleasure for me to introduce to you Munir Naifi, who is a professor of physics here at the University of Illinois. Munir was born in Palestine/Jordan. The boundaries, of course, change from time to time, and he was an undergraduate in Beirut at the American University there. He went on to graduate study at Stanford, and I think we're going to see a little clip of some of that time later on today. Since then, he's worked at Yale University and also at Oak Ridge and Argonne National Laboratories, as well as our physics department here at Illinois. It's a great pleasure for me to welcome him today, and he's going to tell us about scanning tunneling microscopy and other ways really to see atoms. Munir.
Well, it all started with the Big Bang. Some odd 15, 20 billion years ago, there was an explosion. The universe was a point-like singularity, and it exploded. It was extremely hot, and as the universe started to expand and cool, the gravitational force split first, then the strong force, then as the cooling continued, the electromagnetic force and the weak force split off. We were unified here, and now the forces as we know them of today, there are these four of them. As far as matter is concerned in the universe, we started with a molten soup of quarks and other heavy elements and other heavy particles. And then as the system started to cool, quarks and leptons started to become more differentiated as compared to the soup. And then nuclei started to form from quarks. And in this stage of the universe, the whole universe was in a highly state of ionization. A lot of light, a lot of high-frequency light, and the system is like electrified. As the system started to cool further, the very energetic photons diminished, and electron-ion recombination started to take place, forming atoms, neutral. They are actually transparent, and they don't absorb light very much, and so there was a state of a freeze as far as the temperature of the universe. Eventually, we formed from molecules, gas, clouds, stars, and galaxies, and then, of course, living species. We ended up with our Big Mac. Well, how do we detect material? We detect material if it was ionized, as we have seen in the early Big Bang, charged particles. We can use many famous and straightforward detectors nowadays, the bubble chamber, streamer, spark, and proportional counter. They simply ionize material and you could see a track. On the other hand, if we're talking about clumps of matter larger than half a micron, as we have seen in the last state of the Big Bang, then we can use optical microscopy, we can use the naked eye, and sometimes we can use the electron microscopy. On the other hand, the intermediate stage of the Big Bang, where we have single atoms and molecules, this stage is the hardest of all to detect. And that's the subject matter of this talk, to show you the various techniques and other difficulties in detecting atoms and molecules. Here's an example of how we detect charged particles. Here's a bubble chamber and an antiproton coming in and depositing its energy in the bubble chamber like that. And these are the tracks as experimentalists see them. Here's the model where people calculate and try to figure out and computerize what's happening. Here's the proton coming in. And you could see there are a couple of places where there are no tracks from here to there and from here to there, and I've labeled them here in red. These two invisible tracks are for neutral particles. They don't get detected. They don't leave tracks. And you can see they are invisible in a way in such, and you have to kind of do your theory in order to predict these particles. So atoms are hard to detect because they leave no track, they are neutral. They don't respond to electric and magnetic fields strongly. You cannot accelerate it, you cannot guide them. And moreover, they do not appreciably scatter ordinary light. That's why the universe actually cooled and the light is not anymore absorbed and scattered strongly. And they are also, if you find them, they're in constant motion, thermal motion, whizzing around, uncontrollable. Their speeds 200 to 2,000 meters per second at room temperature. They don't have a definite boundary, and they're really very small, on the order of an angstrom. They don't have a shape, really. It's a probability cloud. You learn about that when you go on your career with quantum mechanics. One of the reasons why atoms do not appreciably scatter light is because if they have a discrete structure. Here's an example where I showed you hydrogen, mercury, and neon. And as you could see, their emission comes in discrete lines. They don't do nothing in this region or that region, only on these discrete lines. In fact, every atom has a specific set of these lines. And because they are different, we could speak of them as the fingerprint of the atom. On the other hand, here is a continuous light source, and you could see all the colors in a continuous fashion. These dark lines are actually displayed here to show you that when the hydrogen atom absorbs from this white light, actually it only absorbs over these discrete lines. So most of the light is a waste. Now I'm going to demonstrate for you or show you that indeed atoms do have fingerprints. I suppose everybody's got one of those little gratings, so I'm going to now walk towards that setting here. And if you look at this Christmas tree, you got mercury, you got helium, you got neon, and you got hydrogen. Through the grating, you might have to rotate it a little bit and look to the side. Look through it, but angle your eye. You'll see discrete lines, different sets of discrete lines. On the other hand, if I turn this white light on, now you can see a continuous spectrum. And so indeed, atoms do have fingerprints. They have a specific number of wavelengths. Now, you can continue to practice doing this while I'm talking. That's why we gave you the grating ahead of time. Just look through the grating and look to the side. Look at the Christmas tree and look to the side. Put it closer to your eye and look to the side, and you're going to have to practice at it. And eventually you will see light. You'll see the light. So what do we do? How do we help the atoms do their thing, scatter light, and become visible? Well, it would be nice if we were able to squeeze all that light together closer to one of these lines of the atom. That's fine. Then it turns out that these atoms really have very sharp lines. And it would be nice to narrow it to make it really fine in color. And then atoms do not actually live very long when you shake them and excite them. They don't give you time. They live on the order of 1 to 10 nanoseconds. So you would like to squeeze also that light in a short pulse. Moreover, you would like to focus it. The atom is 1 angstrom. And it turns out if you try to focus light, it's hard to focus. The most you could do is the wavelength, and that's a lot larger. So you would like to do the best you can here. Here's for hydrogen. It shows you all some typical transitions. So that's what we are after. And indeed, that was accomplished with a new in a new device called light amplification by stimulated emission of radiation, laser for short. A lot of us heard of this. What is a laser? A laser is actually an organization of atoms. You organize an atoms in order to do the following: to emit light in a very direction, in one direction, rather than in all directions as ordinary light do. And then you get a high intensity, because everything is concentrated in one dimension. And then high degree of frequency definition. You could get a pure color, red, pure. And then you could get a high degree of coherence. The light is so smooth and doesn't have a lot of noise, so you could focus it pretty well. So we speak of tunability, meaning you can change its wavelength and adjust it to wherever you want. We can make them in short pulses, And well, the fascinating thing is that you can computerize them, and you have a lot of control. Rather than talk to you more about the theory of lasers, I'm going to show you a clip, a video, about 4 minutes, to show you some of the properties of the laser. So please, I got a...
Traditions of America has been the startling productivity of its scientists and inventors. The history of the United States could be written in terms of their contributions. The discoveries of Benjamin Franklin, Samuel Morse and the telegraph, Alexander Graham Bell and the telephone, Thomas Edison and the light bulb, the phonograph and motion pictures, Henry Ford, Wright brothers, Dr. Jonas Salk and his polio vaccine, the collective effort to put a man on the moon. This is a film about 5 contemporary Americans working within this great tradition, 5 who dream and invent. Arthur Shallow, professor of physics at Stanford University, is credited along with C.H. Towns with one of the most important scientific revelations of modern times, the discovery of lasers, or coherent light.
The atoms in the...
Shallow's lectures are popular and entertaining. Students crowd the aisles to hear this brilliant physicist, whom they sometimes call the laser man, explain the principles behind the invention that made him famous.
So this atom emits its light, ping, the waves spread out in all directions. Another one here emits its light, ping, 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 ping. And big ones go, pong, 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 and so you have just a jumble. Reason people call that kind of light incoherent. Now, I mentioned we have light from candle. It's just a hot body. Now, since we'd heard so much...
Shallow's demonstration laser looks like some space-age toy out of a comic book, but it has a serious purpose, to demonstrate one of the amazing properties of the laser beam, its ability to pass through a clear balloon to burn a dark balloon inside.
Except at the zoo, and but the animals at the zoo look awfully big and fierce, so we just bought a balloon for the children.
The demonstration is funny, but not frivolous. The use of lasers in eye retina surgery is based upon the same principle.
Now, they look at that balloon. We found there was a mouse inside it. It's really terrible the way mice get into everything. But we were able to take, so we had to take our more or less trusty laser, and we were able to dispose of it. Lasers produce such very narrow beams of light that they act like the ideal rays of geometrical optics theory. So we can use them to demonstrate the properties of lenses. We can make the beams visible with a little chalk dust and then see how they focus as they pass through the plastic lens.
That's me when I was senior.
Do we have to tilt this, move this end mirror here?
Shallow's seminars with graduate students, including foreign students from places such as Hong Kong and Lebanon, reflect the dynamic atmosphere of a great university. Shallow and his students speculate on new ways to probe the hidden secrets of nature, using unnatural, man-made laser light.
That'll be tricky.
Shallow is interested in finding out how matter behaves, and in finding ways to make it behave differently. One exciting project concerns the possibility of using high-powered lasers to heat a hydrogen pellet until a thermonuclear reaction takes place. If this can be done, then it will provide an inexhaustible source of pollution-free energy, an answer to the energy crisis.
Transducers for the one out here and the one back here.
Shallow's lasers already have many practical applications. They're used to cut titanium, to drill through diamonds, and to cut ceramic plates. In the hands of skilled surgeons performing delicate operations on the retina of the eye, they have saved many people's sight. A laser beam can have brute force, too. It can burn through fire brick in seconds, Or sent through a tube no thicker than a human hair, it could carry thousands of telephone conversations. At the Bell Labs, lasers have recently been used to levitate matter, an incredible feat of scientific magic in which a particle is suspended upon a laser beam in open air.
Well, I would like now to show you how these lasers are used in detecting atoms. In fact, the laser you have seen Shallow describe is the invention, is the first tunable dye laser, very narrow band tunable dye laser, and it actually made the revolution in spectroscopy. Here what we can do, if I got an atom which has its own fingerprints, I can interrogate, detect, and perhaps observe these atoms by shining the appropriate photon, appropriate laser beam, and wait for the light to scatter and go after the scattered photon. This is called resonance fluorescence. On the other hand, if I don't want to wait for the photons to be scattered, I might fire another laser beam which will break the atom apart and bring me an electron and an ion. It produces a charged state. We can go after the detection of the atom and interrogation by either detecting the charged state or detecting the photons. And it turns out detecting the charged state is a lot easier than detecting the photons, and it has a lot more sensitivity. And that goes back to the idea that it is easier to detect charged particles, as we have seen on those bubble chambers and other systems. So I will show you now how a system where I was involved in when I was at Oak Ridge National Laboratory, where we were able to detect single atoms. For example, here is a detector, a cylinder, gold cylinder, a little bit of it gold, and a wire like this. The wire is kept at some high voltage, and the cylinder is at ground. And the red ones are atoms coming in, evaporated from here, and there are other atoms, the green ones, in the detector. A laser beam comes in from left to right and exits out. And the laser beam is tuned and to match the property of the red atom, for example. Here's a schematic. A photon comes in, it hits the atom, it excites it, and then either the same photon, if the design calls for that, or another photon would break it up and producing the electron and the ion. Now the electron and the ion, they're going to start moving towards the wire, especially the electron, and as it moves, it's going to trigger more ionization and it's going to amplify. Now, if we can assure ourselves that every atom is being excited and every atom is being broken up, and if this signal is big enough, then in principle I can detect one atom if there is only one in the path of that beam. And this is indeed what we showed and demonstrated. And when that happens, Physics Today reported it. Here's me, still has a lot of hair. Right there. And it says resonance electron spectroscopy detects single atoms. Now, I thought it's important once Physics Today wrote about it, but I wasn't convinced till the World Book wrote about it. And they showed a picture, here's me and somebody else, and here they made a nice kind of schematic for the detection. And it is not really that different from what Shallow described about the mouse disposal, because here are a bunch of all sorts of atoms, and the only one we are targeting is this green atom. And indeed, all the photons would pass, do not run into the other atoms, except shoot this particular cesium atom, and that's indeed what happened. Well, I tell you what, I'll show you this. I'll show you this. It's a quick one. There's a magazine called Optical Spectra. They started to write about this. And I said, oh, please don't use the unveiling terminology. It's not really scientific. It's more like culture and this like that. Although they describe it here as they say the tenure of the atom as a mysterious entity is indeed short, they insisted on using unveiling. Well, by the time you know it, this magazine really went under, and it's now called Optic Electronics. Well, somebody tried to make money out of it. So they made an advertisement, in physics today. It's called a company called Chromatics, and they thought they could sell more. But by the time you know it, it went under. It could be nothing. I'm not sure what's happening. But there are some good applications. If you can imagine, if you can detect and target one atom and neglect all other atoms around you, then perhaps you could look for so-called rare events. We've just seen how in the Big Bang, everybody now believes that quarks are all tied together and you don't see any of them. However, are there any left over? Really? If there were, where would we find them? Well, they might attach themselves to nuclei, forming some type of weird atom called a quark atom. Here's an example, a sodium atom. If a minus 1/3 quark lands on its nucleus, then it will take its yellow line, the 5890, that's fingerprint for that sodium atom, and will change it to more a red line, 9500 angstroms. So if you have time and you have money, you could sit and look for a weird one like that, and if you do, then you can get everybody in the physics community to believe that there's something wrong with the confinement principle, which everybody talks about. Now, there are other applications, but this one, the particular one I'm going to mention, we really did not think about. But, well, some reporter thought that if this is a very sensitive technique, perhaps one could carry a laser to an ore and look for gold. And, you know, it's very sensitive. And so the Miami Herald wrote an article about it. And a week after that article was written, a request for a preprint came from Florida. And the request says, please send me details of the article entitled Prospectors Could Hit Bonanza with a New Laser Atom Detector that appeared on December 23rd, 1976. Don't ask me whether we made money or not. It's a different matter. So now we have established how we can detect single atoms. However, we don't see them. It's like more like an electronic kind of way of seeing atoms. It's good for science, but it would be nice to look at them with the eye. We have a problem when we talk about atoms. They are in thermal motion. They don't give you really time to look at. They have random velocity. Transit time, if you calculate transit time of an atom across a laser beam, is 10 to 100 nanoseconds. There isn't time. And also, since they are in motion, their fingerprints become masked because of the Doppler effect. And each atom is moving in different direction, giving us a different, and with a different velocity, so it's masked. Well, how do we solve such problems? Well, we can solve them by cooling the apparatus. Just cool down everything. Well, it turns out everything goes down with the square root of temperature, and it's not that great. You can't cool a big device like that and gain. Although people tried, and it was a bread and butter of many physicists and chemists. Then you could do other tricks with these new laser beams, which made a revolution in laser spectroscopy. And you could try to get the effect of the Doppler effect. For example, look at here. Here are a bunch of atoms. You shine one photon from this side, another photon from that side. This side, if an atom is moving one way, this laser beam sees a lower frequency. This side sees a higher frequency. And perhaps if you become ingenious and manage to add these two photons, then you could get rid of the Doppler effect. And that's indeed what people did. In fact, I used this. This was my thesis at Stanford, where we were able to unmask the hydrogen for the first time at room temperature using this new laser, which Shallow was talking about. Now, of course, people are doing a lot better nowadays. For example, now they are going after the atoms individually and cooling them and stopping them. Not the apparatus, big, but the target itself. And so now we'll show you how that works. But before I show you how that works, I'd like to show you that indeed this Doppler effect, which is masking everything, is really for real. Here's a fork, and you could hear the frequency. But if I move it like this, you can see that the frequency changes. And since each atom is moving at its own pace and its own direction, then you know that this is some kind of a masking. So how do we slow these atoms? Well, we have a couple of ways at our disposal. One, we can trap them and cool them in the gas state, and I'll show you examples of that. Or you can actually pin them down to surfaces. Take the atom and put it on the surface, get it stuck. And if you do, then you have a lot of time to look at. You could do that by freezing the atoms on surfaces, just like you see things in winter when they get frozen on windows. Or you could deposit them at room temperature. You've got to be good at that. Or you could make them make a chemical bonding on the surface. So any of those techniques would work. Let's look at the first one. Well, how do we cool them in the gas phase? Well, if you shine a laser beam or some light on an atom, here it is, an atom is moving with velocity v this way, and if you shine these photons on it, it is actually a collision between the photon and the atom. For example, the photon has a momentum. It's energy divided by the speed of light, or h nu over c. The atom has a momentum, mv. So it's like two balls colliding with each other. And when the photon gets absorbed, and if this photon is tuned to the characteristic fingerprints of this atom, and it gets absorbed, then the atom gets pushed, according to the game of billiards. On the other hand, the atom would not last, as I mentioned to you. It will emit back this photon. But fortunately, it emits it in all directions, and therefore there is a net gain. There's a slowing down in this direction, and it picks it up in other directions. So that's the principle of stopping atoms. And I could demonstrate that for you in a minute. Here it is. You don't have to be fancy. You don't have to use a laser light to show that light, an electromagnetic wave, actually push things. Here's a regular light, and here are some panels. I can show you it can push even panels, but I got a lot of photons. Wait a minute, and those panels start to rotate. It's an ingenious device so that when they get pushed, they start to turn. You can see it turns. Indeed, this is how it shows that light, an electromagnetic wave, do push things around. And in fact, if you shine a laser beam on something in outer space, you could make a laser sail, and you could get it to sail for very large distances and over a long time. Here's a diagram of how people cooled things or trap. I start out with an iron, because an iron is easier. Remember, it's an iron is easier to fool with. If you have a ring, and here is a piece of half of a ring to show you what's going inside, a ring with a top cap and a bottom cap, and you put some oscillating voltage source on it, then it creates an electric field, these red arrows, in this form. And if you have an iron somewhere here, then this iron will be pushed around from all sides, and it would tend to stick in this region. This is trapping. You just trap it. Now, it still is whizzing around, so if you shine a laser beam, and if this iron, although it's charged, but it has its own also fingerprints too, you could target a certain transition in the iron and push it, say, in this direction. But since it's bouncing around in the other direction, eventually you can cool it. And then you could look and observe through whatever means you got, your eye or some actual camera. Here's another sort of trap where it becomes even more elaborate, where they add a magnetic field. The blue lines are magnetic fields, and the red lines are electric fields, and they use more lasers. Here's two cooling beams, 1, 2, and this has now become fancy probing. So you could find light and let the light scatter, and then you could see things. And in this region, they have put some mercury ions. And the mercury ions got trapped between the electric and magnetic fields, and because of the magnetic field, they start turning around. And here's a pattern for a plasma. It's very nice looking, and this plasma starts to turn, so you are actually seeing rings. The two laser beams help you cool a little bit better. I'll show you right away an example. There is a single mercury ion. There goes the mercury ion. Can anybody see it? Can anybody see a mercury ion? Anybody see a mercury ion? Raise your hand if you see one. Where is it? That's it. That little dot is our mercury ion, one mercury ion. They put there in that trap, and between the laser beams and the magnetic field and the electric field, it got stuck there. And it's not moving anywhere. Now, when things don't move anywhere, you could think of their temperature as really, really cold, but it's only that is cold, not the apparatus. Well, people got fancy, and they could stop a beam of sodium. You know, sodium looks yellow, as you've seen in chemistry in your classes. A beam of sodium is coming from right to left, moving like this, and a laser beam is running into it from left to right. And you could see the beam of sodium moves, and then stops, because it gets pushed. And the different ones they're just changing the frequency to show you that they can change the place where they stop, to show that, oh, it's the right phenomena we're looking at. But indeed, they can stop a sodium beam. People got better at it, and now they shine 6 laser beams. 1, 2, 3, 4, 5, 6, all intersecting. And there is a lot of sodium in this region. And only the sodium, which is happens to run into this intersection, it gets stuck there. It's like a molasses. It gets pushed from all directions. It can't go anywhere. And there's other sodium here. For example, you could see the streak of sodium. But this is the, and the temperatures could go down to milli or micro Kelvin. Well, this is pretty convincing because I see pictures. I see the ion, I see that, you know, so it kind of looks nice. We got to move on. There's a new technology, microscopy. Now we put atoms on surfaces and look at them. Well, we can look at them with an optical microscope. Unfortunately, we can't do better than 4,000 angstroms. That's basically the wavelength of the bluest I can, you know, find and see with. You could use electron microscopy, where you replace the photons or the light with an electron beam. I'll show you in a minute. And you could do better. You could go down to 20 angstroms. Long way to go with 1 angstrom atom. But the most recent devices are called tunneling, operates on quantum mechanics, although this one operates on quantum mechanics, but this is a neater idea on quantum mechanics, and it can resolve 1/100th of an angstrom. It's overkill, you could say, but that's where it goes. And then we have another force, an atomic force microscope, which is 1/100th of an angstrom too. And one salesman told me they never say the word atomic force when they're carrying one on an airplane, because they run into trouble. They always ask him, what's that? They give a different name. Sounds serious, but it's the most harmless device you could see. Here are schematic of some of these microscopes, an optical microscope, an electron microscope, and an SCM. This is the one which does really the best nowadays, 20 angstroms. Well, what are these? Well, I want to just point out to you or remind you of 2 things. One is that in electron microscopy, you have an electron gun. It's somewhere here, and the sample is way down there. It's far away. The same thing with the scanning electron microscope. The electron gun, there's always a gun, shoots the electron, and the sample is way down. Okay? Well, that's the pitfall of these microscopes. I don't have to tell you about the optical microscope. You've already seen it, and you know what's its limitation. And what's the new invention? This is the quantum-based microscope. And this is what happens. Instead of using a gun, you use a needle, a sharp needle. It's not a gun. No electrons would come off at any time until I do my thing. And so there are no gun. And then on the other hand, the sample is put here. That's the first thing you do. The second thing you do, you bring the needle and the surface close to each other, very, very close. What's close? Closer than you think, maybe a few angstroms. Producing a narrow gap. Here it is. And the gun, which I don't have, is a needle, is cold. No thermal or field emission at all. When the needle gets close enough to this, electrons start to jump through the gap, just like you are jumping from one mountain to another. You've seen those commercials sometimes. If you don't jump, you fall down, you're destroyed. And so you jump. And the question is, the closer you get, the better the probability that you're going to make it. Like if you can either jumping over something. I mean, jumping through. Now, it turns out that the jump is a quantum mechanical phenomenon. It's called tunneling. You study about it later. We don't need to go into depth into this. But something is important. The dependence on the distance is very, very sensitive, exponential. What do I mean by that? I mean that it makes a large difference if the gap changes by only 100th of an angstrom. Well, how much change? It makes about 2% in the probability of jumping. That's important. I can measure 2%. I can measure 1. And so that's what I mean by we can get resolution of 100th of an angstrom with this device. Well, how does it look? It looks like this. I enlarged everything. Don't worry. These are really sharp. This is the tip, the sharp needle, and we put it on mechanisms to move it around, to control it. So piezoelectric drives. You put electricity on them, they expand, they contract. You know, you could control. You bring it close to a surface, and here I'm showing you a surface, a typical surface of a solid. Or if I may, I could show you a couple of examples right here. This is graphite. That's how it looks. So the atoms over there looks like those. This is sodium chloride, the stuff we eat. And this is, I said, diamond. In real life, it looks a lot nicer, black. And so typically, you bring in your tip, like my finger, and you get close, like this, and you start going over it. That's all you do. So, as we skim the tip of this microscope across the surface, you could see that the topography of the surface, one atom up, one atom is down, and as the tip is moving, the probability for the electrons to jump is going to vary. For example, right here, the atom is depressed, so the distance is more, so it's going to get less current. Here, this is a protrusion. There's more current. And so if you plot the current as a function of distance, you're really plotting the topography. Well, the people do a little bit better than that. They actually hook it to a computer and hook it to a feedback loop, and instead of measuring the current, they actually do a real thing. They fix the current, and they say, I want this number of electrons to go through, and they let this thing kind of swim up and down to keep the current, and indeed, you see it like an airplane flying over mountains. When you hit a mountain, you fly a little bit over. You don't want to run into it. And you go down to a ditch, or you go down, and that's exactly what it is. It's a flying kind of device. Let me show you some examples of what you see. Here is a surface imaged by the scanning tunneling microscope, and it shows iodine atoms. These pink iodine atoms are sitting on a surface of platinum. I don't see the platinum atoms, but I see the iodine, pink. And these are false code for colors just to make the thing, the iodine atoms may not look like pink. I could change this whole thing into blue and orange and all of that. But in any case, you see an iodine atom sitting in some kind of an orderly manner on the surface. How do I know that these are iodine? I don't know. I'll say more about that in a minute. Here's the surface of diamond or silicon, which looks like that. I don't want to make this drop because it's expensive. Now, this STM tip can act like a hand. A hand. So I invented this. This is an IBM thing, but I invented a title for it. I call it atomic Lego. So what they do, they take xenon. Xenon doesn't stick to anything, so they cool it. They cool a nickel surface, and they have xenon in gas. Then xenon, lands on this and sticks like in a random way, like this. So they come in now with the STM tip and like a hand, and they pick each one and move it around according to their motion, big hand, small hand. And they were able to write to IBM. So it's a Lego. It's pretty neat. They got a lot of publicity for it for free. What we could do, we could add a gas. If you take this tip, sharp tip next to the surface and put some gas of choice, and even put a laser beam there, what you could do, you could interrogate this gas with a laser beam, change its wavelength and and select a certain material the way we were using the fingerprints. And then by selecting this material, you could help the tip now with the laser to push ions, because the tip is biased, positive, negative, so you'll be able to push ions, positive ions, onto the surface and give them just a little bit, maybe 1 volt, so that they would just stick. It's like a bullet going in. And so you could do that. And this is what we've done here at Illinois in our laboratory. And we were able to push one single molecule. It's a complicated molecule. It's called trimethyl aluminum. But if you actually look at the charge, at the electrons coming up from all of these atoms, I'm not a chemist, but if you look into a chemistry book, you'll find that the electrons make 2 clouds, one here and one there, with nothing in between, a node. And so when you force it to the surface, and here's the surface of graphite, you see these are at graphite atoms, like this. And with what we've just done, we just put a molecule right on top of it, and it looks like a cloud. And this is, you see the node. Now, can I really tell that this is a trimethyl aluminum? Well, I don't have resolution of the individual atoms, as you could see, but if I know what I put, I can verify it. And so the science has not yet advanced enough to identify an atom sitting on the surface, and for a good reason, because once an atom sits on the surface, it loses some of its properties. It gets pushed by the other atoms around it, and unless you calculate and do all sorts of things, you won't be able to say that's hydrogen, because I only know hydrogen is sitting in the gas phase. It has its fingerprints. It loses some of its fingerprints when it sits on the surface. You might have seen this quantum coral. IBM people were able to take 48 iron atoms and put them on a copper surface. And here's one atom, 2, 3. Actually, I counted them, 48. Go around like this. They put it in a neat way with the STM. They pick in one, put it in. Again, these iron atoms won't stick very well, and they move around, but they've done it at 4 Kelvin, down in temperature, and make them to stick. Unlike the molecule which I showed to you, because we pushed it in that room temperature. So this is lower temperature. And you can see it makes some sort of a ring. And the ring makes also ripples. 1, 2, 3, 4, 5. And those ripples are the cloud, the electronic cloud in the copper surface. And indeed, this is in agreement with what you expect from simple quantum mechanics, a circular quantum well, or box, a circular box. You study about that in first year freshman college. Here's a good one. Here's a good one. This one we made in our laboratory here, and it's a heart. I was trying to sell it to Hallmark, and the title would be, I'll give you the smallest heart I can get. Hey, when we made this one, that was a hit, because love physics, everybody liked that, but other people started saying love Phyllis or love Philistine, whatever you want. It's pretty small. Well, we want to do something with this technology. We just can't, this is a hoopla, and okay, it's good to make graffiti and run around, and now everybody writes the name of their university, U of I, we wrote UI, and everybody around the country write their names and write everything in atoms. So this is New Scientist magazine, comes out London. It says, nanotechnology rules. Creating microscopic graffiti is fun, but for the people working in atomic electronics, the serious business is devising minute devices for the future. That's the idea. And they showed some neat examples to show you that people now can do things. Here's a molecular man by IBM. Here it is. And this is made of carbon monoxide molecules. They just stuck them like this with hands and this. Here's the love physics from our laboratory. And here is a CD disc. These two are the music, the etches on the disc produced by the laser. And at the University of Basel, they wrote something, Eureka, in between, to show you that they could do better and things are moving along, okay? Here people, the IBM made the map of the world with atoms. Oh, the other part is on the other side of the world. Well, here's what, you can't believe this. I don't think you would be able to believe this. This is the Stanford logo, 75 micron across, and see how much detail. This is, of course, enlarged quite a bit to be able to see such details. It's unbelievable. And during the Gulf War, the Japanese, always for peace, they wrote on silicon, by taking out silicon atoms, they wrote, I don't know whether if you squeeze your eyes, you could see peace 91 HCRK. That's the Japanese laboratory. Do you see it? Look at the dark stuff and you could see, you could spell the word peace. That's before the Gulf War. And the magazine also reported the thinnest line ever made in my laboratory, which is on silicon, which is 5 millionth of a millimeter wide. And you could imagine, we could come in and fill this line, this groove with niobium, with copper oxide, with what have you, in order to produce, additional. And they, of course, they showed the single molecule. The magazine saw fit to use its cover for the feature, and you see the piece, you see the heart, and you see the molecular man, and you see the symbols of atoms, circuits, and that's the idea that the future is using atoms and molecules to make devices. And they called it the smallest graffiti in the world. But since I got a few copies of those, I started looking, I saw the 3 other interesting topics. Women in technology, the secret sex life of fungi, and when the solar wind blows. Look it up, they're really interesting. I'm not kidding. This came out of London, this magazine. And there was a London daily, in a language you may not be able to read, picked up the heart. Picked up the heart like this, and they wrote an article about it. Don't worry about it, that's my name, really it is. Okay? Well, this daily in London, this is the second part of the continuation, is Al Hayat. It was in the news recently. The letter bombs. You've heard of the letter bombs or arriving in this country? It was for this daily. I don't know what's going on. It could be nothing, but every time I see these atoms, something happens. I mean, this is a sad, but I'll show it anyway. This is the late Rabin, and the heart and the atoms are on the same front page when they received the Nobel Prize. Could be nothing, again, but now, now what sort of devices we can make out of these? Here is the simplest of all of the devices. The so-called the tiniest switch in the world. Tiniest switch in the world. And it's basically made, well, I tell you what, IBM people love xenon. And in fact, the IBM administration or management, they hate xenon. Because xenon, you have to cool everything, and their equipment, they're never cooled. They want things at room temperature. But the scientists love xenon because they could do something with it. But it's impractical. It's useless if you have to do it at very cold temperature. But in any case, this is a xenon atom on the tip of an STM close to a cold nickel surface, the one they were writing on IBM. And the idea is that this is, they call it a switch, the fastest switch. It's on when the atom is here, and when they drop the atom on the surface, it's off. Well, how do they drop it or take it on and off? By firing a voltage. So the atom is moved by applying a short voltage to the tip. And the positions between up and down are interchanged by reversing the polarity of the pulse. So that's the raw definition of a switch. There's a new idea using zeolite. Zeolite molecules are quite interesting. They look like a soccer ball, but not like those carbon-60. And here's a zeolite molecule. And it's basically, zeolites are made of aluminum silicates, SiO4 and AlO4 connected like this. These are usually, these zeolite materials, they come in with cages. You could look at this as a cage. And now if we trap some kind of a molecule inside this cage, now you could bring the STM from the top and push the trapped molecule from one location to another. And you may call the position where the molecule is sitting right here is an on, and push it to this side, it's an off. So it is basically now a little bit better of a switch because the STM is not actually part of the switch. It just pushes on and off. And this is actually under consideration by different groups around the country. But a new device, which we are at the U of I are looking at, is trying to use wave-like electrons to develop a device called a quantum interference transistor, a transistor that works on quantum mechanics. What is that? Here's a quantum interference transistor, the idea. You start out with a silicon substrate, here it is, and then you put on it two contacts. Here's one, the dark one, and here's another one, facing each other. And you get the contacts closer to each other by providing two fingers. It's hard to bring the big ones, so you make two fingers. And hopefully you bring the fingers as close as you could get and create a tiny little gap. Here's an enlargement. Here's one finger, the dark one, and here's the other finger. These are the two fingers. And now what happens that the electrons can flow from one contact to the other through the channel, which I call this one the channel, which is the gap between the two fingers. That's basically the idea of a MOSFET transistor. Then what we do, we implant patterns of other atoms, shape of wires, gratings, or grids in the channel region here. I show one diagram of a wire, a schematic of a wire. This is a real picture. It is made by the atomic force microscope, which I did not describe to you how it works, but basically like the STM, but it operates instead of tunneling current and though it operates on forcing, static, actually repulsion of material on material. It's quite sensitive too. And it's useful in making measurement of things that are not conducting and don't have electrons jumping from one to the other. Now, if you cool this device, well, we got a cool here at Illinois anyway. If you cool this device to around liquid nitrogen or slightly above, you'll find that the electrons will have a wavelength, a quantum mechanical wavelength, will behave as waves of 10 nanometer wavelength. And then as the electrons move from one side to the other with the wavelength, you know it, they start diffract and interfere and all of that phenomena. And the idea here is to exploit such processes as interference and diffraction to control their flow and to get quantum mechanics to do the job. Now, what's good about this? First of all, it is faster. It could be faster than an original or a conventional transistor. Why? Because I could bring these two fingers even closer. I could close this gap more and more and more, which means electrons would have less distance to travel. That minimizes time. Secondly, it consumes and dissipates less energy. Why is that? Because if electrons behave like waves, they don't scatter as much from the substrate and from the material they're running into because they are waves. If they behave like particles, they will scatter and lose heat. So that's the idea. This is the next sort of generation of devices. And here is a schematic of what one could do. This is the finger and the other finger, and now you could put more lines and really do a grating so that when the electrons go from one side to the other, they actually not only see one or two lines, they can actually utilize the resolution of a grating. You know a grating has a higher resolution than a two-slit problem. The more the lines, the higher the resolution and more control. And here you could go grid in 2 dimensions. You could make resolution in either this way or that way. And so these are 2 active areas under consideration in our laboratory. Here's an actual finger-to-finger, and we try to put atoms in between, aluminum atoms, to make these wires. it's, you know, in nature, it's hard to see big and small at the same time. So my students, Jim Hetrick and Alan Archer, were trying to do their best in order to make us see the atoms while we see the big contacts, because you could either see the big contacts well, or you could see the atoms well. And so here they found an orange color, which is beautiful, and they show that we were able to put one quantum wire, another, and one in here. And so it's really going on very well. And I could tell you about another application or a couple of other applications. It all started with a Big Bang. Do you want to go through it again? Maybe not. And so I will end the talk by writing with atoms an E for end. And thank you very much for your attention.